conservation of momentum. As we saw in the earlier discussion, as per second law, force was equal to mass into acceleration, and we could derive that force is equal to change in momentum by time. When F is equal to 0, delta P, change in momentum, must be 0. So what it means is, if there is no net external force acting on the system, the momentum of the system should be conserved. Let's take a simple example, that an object of mass m1 going at velocity v1, another object of mass m2 going at velocity v2, and this constitutes our system. So what is the initial momentum? m1 v1 plus m2 v2, P initial momentum. Let's say for some reason they collide internally, and then the final system looks like m1 going at v1 dash, m2 going at v2 dash. So final momentum should be equal to m1 v1 dash plus m2 v2 dash. Since there is no external force, F external is equal to 0, hence the momentum of the system will conserve, and therefore P initial equals P final. That means m1 v1 plus m2 v2 should be equal to m1 v1 dash plus m2 v2 dash. This is what we mean by conservation of momentum when there is no external force. Even though these two objects internally they collided and they changed their velocity, but still momentum of the system was conserved. So this is what we mean by conservation of momentum, and this concept can be used for solving any problem related to collision of two particles. In fact, when there is no loss of momentum, we call the collision as elastic collision. If there is any change in momentum from initial to final position, it is no more elastic collision, and it's partly elastic, partly plastic collision, which is out of discussing plastic collision is out of syllabus for CET, so we'll restrict ourselves to elastic collision. So in case of elastic collision, momentum of the system is conserved before and after collision of the particle. So that's what we had to discuss in case of conservation of momentum. Now let's talk about frame. So we have two types of frame. One is inertial frame and another one is non-inertial frame. So whatever Newton law of motion we discussed is applicable only in inertial frame. So Newton law is applicable in this, whereas in case of non-inertial frame, Newton law is not applicable. Now what I mean by inertial frame and non-inertial frame, let's take an example. Let's say we have a system where an object is hanging from the roof and an observer is sitting. So observer is also part of the system, and now entire system is going down with acceleration A. Now when this observer looks at this hanging object, now observer is no more stationary. Observer on its own is moving with an acceleration A, and this becomes a case of non-inertial frame. Whereas an observer sitting on the ground, when he looks at the entire system, he is not moving with the reference to the system, so he is in inertial frame. So if this observer wants to write or applies Newton law of motion for this system, he should get the equation right. But if a non-inertial observer applies Newton law of motion for the subcomponent of the system, he gets the equation wrong, because Newton law of motion is not applicable in case of non-inertial frame of reference. So if we have to make Newton law applicable in case of non-inertial frame, how do we go about it? So we have invented a new force called pseudo force, which is applied on the system to make it inertial frame, and then Newton law becomes applicable in the system. So for example, if this object wants to write a free body diagram, that means application of Newton law of motion on this hanging object, let's look it in this way: mass m, so downward force mg, if there is tension, so T. So if we do not consider pseudo force, the observer gets T equals mg, which is not correct. This is not correct, because he did not consider, in this case we haven't considered pseudo force. But if we consider a pseudo force which is equal and opposite to acceleration, so if acceleration is downward, we apply a pseudo force which is mass into acceleration in the opposite direction. So what it means is, if that pseudo force is transferred on this mass, we have a pseudo force acting upward, which is mass into acceleration of the frame. And now equation looks like T plus mass into acceleration, which is coming from pseudo force, is equal to mg. Therefore T is equal to mg minus a. And now we get the correct expression for tension in the string. When A goes to G, so A becomes equal to G, that means we are talking about a free falling body or a system. Tension in the string becomes equal to 0, and this is a case of weightlessness in the system. Now let's take some problems to explain this Newton law of motion. So here is a simple example. We have an inclined platform where we have a mass m1 hanging with a string which is connected to a pulley, and on the other side we have a mass m2. What we are saying is system is in equilibrium, that means m1 or m2 is not moving. So the task is to find what is the angle which is theta to create this equilibrium condition, and the second task could be to find the reaction force acting on mass m1. So how to solve this problem? So as I said, let's create a free body diagram. To create a free body diagram, we need to assume tension in the string, which is, let's say, T. So the same string goes all around. We are assuming right now no friction in the system, so the same tension continues in the string. Now for m2, it is m2 downward force m2g, upward force T, therefore T equals m2g. Now coming to m1, the gravity force acting downward, which is m1g, string acting, pulling it upward with tension T. So a normal component on this plane, which is this guy, m1 g cos theta, because this angle is theta. In the inclined plane direction, it is equal to mg sin theta. This is m1g cos theta. So to balance this force, there must be a reaction force from platform on m1, which is L. So let's take a force balance in the inclined plane direction. Therefore T becomes m1g sin theta. Now we know T is equal to m2g equals m1g sin theta. G and G cancelled, so sin theta equals m2 by m1. Therefore theta equals sin inverse m2 by m1. This is what we are looking for. Now reaction force, that is N. So creating a force balance in the perpendicular direction to the inclined plane. So N equals m1g cos theta. This is what we are looking in this problem. We could take one more problem. Let's take a simple problem. We have a mass M connected by a pulley and then string pulled by a force F. Assume that mass of the pulley is 0. So the question is, find acceleration of mass M and acceleration of pulley. To solve this problem, let's create a free body diagram. So again assume that tension in the string is T. So force free body diagram for pulley, T, another T and F. So from here 2T equals F, therefore T equals F by 2. Now for mass M, downward force mg, normal reaction N. We are not considering any friction, so friction force ignored. Now this is T. So we find that there is a net force acting on mass M, which is equal to T, and hence it should produce acceleration, so which is equal to A. So acceleration in the mass M is equal to T by A, T by M. Now T equals F by 2, so F by 2m. Therefore A is equal to F by 2m for mass M. So this mass has an acceleration A equals F by 2m. Now what is the acceleration of the pulley? Let's look at the assembly. When pulley moves by x distance, it has to release the string by x plus x distance, and hence this mass which is connected at the end of the string must be moving by 2x distance, and hence acceleration of pulley must be half of the acceleration of mass by 2, and hence this goes to F by 4m. So this is how we could calculate acceleration of mass M and acceleration of pulley. Though the logic we are using is, when pulley moves by distance x, mass M must be moving by distance 2x, for the simple reason that pulley is connected by two strings, whereas mass is connected by the single string at the end. So this is what the logic is. Let's now discuss about friction, which is related to Newton law of motion and free body diagram. So take an example, mass m1, another mass of m2 is kept on it, and there is a contact between m1 and m2. Now when m2 tries to move in any direction with reference to m1 tries to hold it back. So basically we develop some sort of friction at the contact surface between m1 and m2. So if we draw a diagram like force F is applied on m2 and it is trying to move in this x direction, there will be an opposing force which is called friction force to hold it back, and that's how we define the friction. So basically whenever we have two surfaces coming in contact and there is relative motion or a tendency to develop relative motion, there will be friction force existing. Now friction force could be of two types: kinetic and static friction force. Coming to the same example, if a force F is applied and it is not able to move the object or mass m2, the friction force developed is called, so for example case when m2 is not moving with the reference to m1, the friction force F is static friction force. Second case, when the force F becomes too large and V becomes positive or negative, that means there is a relative motion between m2 and m1, the friction force becomes kinetic friction force. So let's understand a little bit in detail what is the meaning of static friction force and kinetic friction force. Let's say we have an object kept on a surface and its mass is m. So a downward force acts, which is mg. Reaction force is equal to n, therefore n is equal to mg. Let's say we apply a force F. If we plot the force applied versus friction force, so when force is 0, there is no tendency for this object to move with reference to the platform, so friction force is 0. As we increase applied force, there is a tendency to move this object, but this object is not able to move, so there is a corresponding friction force developing, and like this trend continues. So as long as object M is not moving because of the applied force, friction force must be equal to applied force. As soon as this equilibrium goes in favor of F becomes greater than friction force, this object will start moving. So the point at which point at which friction force becomes, or the applied force is about to exceed the friction force developed, this limit is called limiting friction force. And we are still in the zone of static friction because object is not yet moving. As soon as the applied force becomes more than the limiting force, object will start moving and friction force will drop little bit and it becomes a constant value, and this part is called kinetic friction because now there is a relative motion between object and the platform, and this point onward the applied force has exceeded the limiting friction force which is developed due to static friction. So this reason is F static. This point is known as F static max or a limiting friction point. So if an object is stationary and an external force F is applied, to move the object F must be greater than friction force static max value, greater than equal to, or ideally it should be greater than this, then the limit breaks and it starts moving. So this is how we define static friction and kinetic friction. So kinetic friction exists when there is a relative motion, static friction exists when there is no relative motion. Now let's see some additional example in terms of value. So friction force is defined as friction coefficient into normal force. So in this case, for example, normal force is mg and let's say friction coefficient is mu, so friction force equals mu into n, which is mu mg. Now mu could be static friction coefficient or kinetic friction coefficient depending upon the condition we are talking about. So if it's static case, mu should be used from a static part of it. When there is a relative motion, then we should use the kinetic part of it. When we are talking about a static friction, we need to be careful because friction force cannot exceed, in no circumstances friction force can never exceed the applied force. So there is a possibility when we are talking about a static force, static friction, if we use the maximum value of friction coefficient for a static, we may get higher value than what is applied force we have for the friction force, and that should be avoided. We should always reduce the value of mu static so that mu static should be equal to applied force. In case of limiting friction force, F becomes mu max into. So this is how we define or we calculate the friction force for a given system. Now let's talk about angle of friction. So take a simple case of mass m kept on a platform. So downward force mg and reaction force c, but when you apply an external force m, mass mg, downward force, and external force F, we cannot have reaction force in the perpendicular direction because we need to have a balance for the F. So it will be an inclined C with an angle theta. So this angle by which this normal force will bend is called angle of friction. So this theta is called angle of friction. Now what is the value of theta? Let's calculate that. So component of C in the normal direction, which is n is called C cos theta, and component of C in the horizontal direction, which is F is equal to C sin theta. We know that mu, which is friction coefficient, equals F by N. F is equal to C sin theta by C cos theta. C and C cancelled out, so tan theta. So mu is equal to tan theta. So basically there is a relationship between coefficient of friction and the angle